Ladies and gents, and welcome to Solving One-Step Inequalities, Chapter 12, Lesson 2. Go ahead and pause, take a look at your homework, come on back when you're ready. So, ladies and gents, let's start. Once upon a time, we learned what a solution was. Solution was a number or numbers that made any mathematical statement true. Then, we found or solved that equation. We found what the solution was. But generally with an equation, there was only one solution. There was only one number in the entire universe. For instance, x plus 3 equals 10. Okay, the only number that will make that a true statement is 7. 7 plus 3 equals 10 is a true statement. But then we got to inequalities, and we realized that inequalities have billions and billions of solutions, and that's just the beginning. And instead of drawing billions of dots, we would actually fill in a line. Now, sometimes the number cannot be true at -4. If, however, it said greater than or equal to, then we would color that in, because -4 is in fact equal to -4. That's a true statement. All right, so that's where we've been. Where are we heading? Let's find what that missing number is. And of course, that will move eventually into two-step inequalities or multi-step inequalities. Furthermore, we're going to realize that while you can sit here and graph on one variable number line, sooner or later there's going to be two variable number lines, and we're going to learn that, not surprisingly, there are still billions and billions and billions of solutions that make a statement true. So instead of drawing billions of dots, we'll have to shade that entire region in. All right, but that's where we're heading for today, solving one-step inequalities. Pause, fill out your paper, come on back when you're ready. All right, now, just like solving, let's talk about adding and subtracting, addition and subtraction inequalities. Just like solving equations, we want to isolate the variable. That means we want that variable by itself. For an equation, oftentimes it would look like that. X is equal to 3 1/3. For an inequality, we're still going to want to get x by itself, but in this case, it's going to be an inequality, an unequal sign in the middle. All right, now, I want you to think about this. I want you to subtract 2 from each side of the inequality. -1 is less than 2. So think about -1, go down 2, subtract 2, you end up at -3. What about 2? 2 subtract 2, you end up at 0. And guess what? It's still a true statement. So when we add or subtract, the inequality sign does not change. Little foreshadowing there. Think about that later. I'm planting the seed. But let's go ahead now and let's actually solve the following inequality. All right, so we want to isolate that inequality. We want to get y by itself. Some people even draw that bar through the middle. So let's go ahead and get rid of that plus a -18. How do you get rid of a -18? With a +18, of course, but we must be fair to both sides. In this case, -18, +18 makes 0. Not that you have to write 0. Hey, look, y is by itself and alone. Remember, please, that when adding or subtracting, the inequality sign does not change. So it's still going to be a y is greater than -26. Go down 26, go up 18, still in the negatives. All right. Now, I'm going to go ahead and just draw a little dot and -8. And I'm going to ask myself, what number or numbers will make this statement true? Now, many times people start at 0. So if I were to rewrite this inequality, let's go ahead and take a number and put it in, and let's just see. 0 plus -18 is -18. True or false? Well, -18 is not greater than -26. That's a false statement. Let's try -3, shall we? -3 plus -18, -21. Is -21 greater than, no, that's a false statement as well. Let's try -7. -7 plus -18, -25. Close, but still not true. So let's go to the other side of the inequality. Let's try -10. Negative 10 and negative 18, negative 28. Wait a second, Mr. Callan. All right. Let's ignore that part of the video, shall we? And start again. Focus on your negatives, Mr. Callan. 0, negative 18. Is that greater than negative 26? Yes, it is, because that is larger than neither one's good, right? Negative 18 is not good. Negative $26 is not good, but I'd rather have negative $18 than negative $26. This, ladies and gents, is a true statement. All right, so let's go back and let's color that in as a true statement. How about a big old number? How about a positive 5? 5 and negative 18, negative 13. Yep, 5 is a solution. How about 9? 9 and negative 18, that would be a negative 9. Is negative 9 greater than negative 26? Also true. How about negative 7? Negative 7 and negative 18, negative 25. Now they're close, but still negative 25. Theoretically, that's more money, or at least less debt. And so negative 7 works. Now, if you went to the other side of the inequality, say you tried negative 10. Negative 10 and negative 18 is negative 28. No, negative 28 is not greater than negative 26, nor would this one or this one or this one. Yes, folks, you can always try fractions in the middle, right? So what if I tried negative 5.5? Let's make it interesting, negative 5 2/3. This is negative 23 2/3, which is still bigger, better, whatever. Negative 5 2/3 works. And so, look, folks, all these numbers are going to be solutions. And I don't really want to sit here and draw billions and billions and billions of dots. So let's go ahead and draw a big, old, thick line, starting at negative 8 and going to the right. Now, the last number I'm going to check is negative 8 itself, although some of you might have graphed that immediately. True or false? Negative 26 is greater than negative 26. No, it's equal. It's not greater. So this is a false statement. And therefore, you should not color that dot in. It should be an open dot. So to summarize this problem, we solved and we found that any number would work. Any number will be a solution as long as that number is greater than negative 8. We've written the answer as a number statement, and we've also graphed the solution set as a ray, starting at negative 8 and going to the right, but negative 8 is not itself a solution, so we did not color in that dot. Now, I took a little longer with example 1. We're not going to take as long for example 2. How do you get rid of a positive 8 with a negative 8? Some of us like to write subtract. Some of us change subtract into add the opposite. Either way, an 8 and a negative 8 cancels out, leaving us with less than or equal to 10. Now, as you can imagine, 9 is going to be less than or equal to 10. 8 is going to be less than 8.5. 7, 6, 5. All those numbers starting at 10 and leading to the left. Now, last thing we're going to check. Let's go ahead and check 10. If I substituted in 10 plus 8, and 10 and 8 is 18, true or false, 18 is less than or equal to, yes, it is equal to. Remember, that word or means it only has to satisfy one of the requirements, one or the other. In this case, it is equal, so that's true. Therefore, we are going to color in that dot, and I'm going to just make it big and loud and proud. So, the solution statement to solve that inequality, any number n works as long as that number is less than or equal to 10. And the graph of the solutions, solid dot at 10, an array leading to the left forever and ever and ever and ever and ever. Onward we go. Let's get rid of that negative 3. In fact, some of you change it to a negative 3 with a positive 3. And let's be fair to the other side as well. Negative 3, positive 3 cancel out, greater than or equal to negative 2, which means we need a solid dot at negative 2. And because all the numbers greater work, Again, anytime you want to test it. A little disappearing ink here. Let's put in positive 6. 6 minus 3 is 3. Is 3 greater than or equal to negative 5? You bet. Let's put in something over here. Let's put in negative 9. Negative 9 minus 3, go down 3, makes negative 12. Is that a true statement? No, it is not. Verifying that all these numbers over here will not work. So final solution statement, any number h works as long as that number h is greater than or equal to negative 2. And a graph of all the solutions, solid dot at negative 2, leading to the right, billions and billions and trillions and trillions and trillions of answers. I'm going to skip this example, ladies and gents. Let's go on to multiplying and dividing, right? So I want you to think about this. Let's put a symbol in here. 6 divided by 3, 2. 12 divided by 3, 4. Still less. All right, let's try another one. 6 divided by 2, 3. 12 divided by 2, 6. We're going to keep comparing the quantities after we divide. Let's divide by 1. 6 divided by 1, 12 divided by 1, still less. Now you can't divide by 0, right? Impossible. So let's try a negative 1. 6 divided by negative 1 is negative 6. 12 divided by negative 1 is negative 12. And how does negative 6 compare with negative 12? Negative 6 is greater. That's weird. Let's just keep exploring, see what happens. Let's do another one. Okay, this is another divided by a negative. 6 divided by negative 2 is negative 3. 12 divided by negative 2 is negative 6. How can we compare negative 3? There it is again. The inequality sign here is going to be greater. Weird. Maybe it's just two exceptions. 6 divided by negative 3 is negative 2. 12 divided by negative 3 is negative 4. How does negative 2 compare to negative 4? No? Okay. I want you to examine those relationships. I want you to note what happens once we divide it by a negative number. What happens to that inequality sign? It flips around. So, the multiplication and division properties of equality states, if you multiply or divide each inequality by a positive number, leave it alone, unchanged. But, and here's the biggest part, the most important part of today's lesson, if you multiply or divide each side of an inequality by a negative number, and that's multiply or divide, not add or subtract didn't change anything, it always flips around, it reverses on us. So if you have a less than, it'll turn to a greater than. If you have a greater than or equal to, it'll convert and flip around to a less than or equal to. Let's see how that works here. All right, so we want to get rid of division. We know the opposite of division is to multiply. Some of you prefer to put a 1 right there, and that's your call. But notice that multiplying by 1 doesn't change anything. Now here we go. 4/4 cancels out, leaving us with a single t. Negative 2 times negative 4, the opposite of all those negatives would be repeatedly going up or positive. Whoa, here we go. As soon as we multiplied by a negative, that inequality sign flips around. So our solution statement here is any number t will work as long as that number is less than 8. I'm going to draw this. I'm going to extend that line. And does 8 work? No, it does not. So I'm going to draw an empty dot. Let me see if I can bring that forward. Hopefully that'll make things a little prettier, huh? There we go. Now, if you don't believe me, come off to the side and try any number you wish. So let's go with a little disappearing ink here, and let's try 4. 4 divided by negative 4, negative 1. Is negative 1 greater than negative 2? Yes, it is. Verified. Let's try something on the other side. Let's go even off the graph. Let's go to 12. 12 divided by negative 4, negative 3. Is negative 3 greater than negative 2? No. And of course, you could try 8. 8 divided by negative 4 is negative 2. Is negative 2 greater than a negative 2? No, it is not. Thus, we do not fill in the circle. All right, a couple more examples here. Inverse of multiply is to split it up or divide, but notice that if we just do that, it'll say the opposite of x, and who wants to know the opposite? So let's divide by not just a 3, let's divide by 3, and then take the opposite. In this case, x is going to be, as soon as I see divided by a negative number, divided by a negative, flips that inequality sign around. 12 divided by negative 3 is negative 4. So this says that any number will work as long as the number is greater than negative 4 and it cannot be precisely negative 4. It could be negative 3.999 and it'll work, but not negative 4. Look at how these problems are similar. Look at how they're different. Inverse of multiplying by negative 4 is to divide by negative 4. As soon as I hear divide by a negative, inequality sign flips around. And so this leaves x less than or equal to negative 2. Now, because it can't equal negative 2, let's make that a solid dot, as well as all the numbers that are smaller or less. Negative 3 works, negative 4 works, negative 4 trillion works, negative 2.00001 works, and so does negative 2, but not negative 1.999. That's what I have for you, ladies and gentlemen. Go ahead and take care of your homework. Let me know if you have any questions, and let's grow.